Welcome, everybody. Welcome, everybody. We'll get started a few minutes early since the room is full. And I want to give our distinguished speaker today as much time as he needs to talk about all the wonderful things that are going on. Welcome to the 7th out of 8 special talks by Berkeley Turing Award winners who have done their work to win their Turing Award while they were at Berkeley. So today I'm honored and to welcome my PhD advisor, William Velvel Kahan, to be the speaker, who won the Turing Award in 1989 for his work on the IEEE floating point standard. So every computer that's basically been built since then does arithmetic his way. And so, rather than entirely rehashing this history, I think we're going to hear a talk looking to the future and what all that has to do with machine learning. So let me turn the floor over to Velvel.
Thank you. Okay, first let me say that you can read this at your leisure. It's on my webpage. And it's all written in English, so you don't have to guess what's going on. And here is the abstract, which you've had a chance to read. Now, I've been in Berkeley for almost 50 years, so I'm accustomed to being interrupted. And if you want, interrupt me, it won't derail the talk. Now, when people think about artificial intelligence, I guess they really think about an intelligence competing with our own. And that's been on some people's minds for a long time. And there are a number of interesting questions. The question that might be most interesting would be if we program some computers, like Rodin's thinker, and program it so that it would think the way we do, what would it be thinking about? I have a guess. It would be thinking about sex, reproduction, procreation. And I don't think we're anywhere near that. I think that artificial intelligence faces a number of difficulties that we have yet to overcome. It may take a while. And here are some of them. Now, I don't say that every application of artificial intelligence is plagued by one of these difficulties, but from what I've seen, a lot of them are. And I'm going to talk about those. The first three are, you might say, strategic. Some have said philosophical, but I'm not a philosopher, so I'll stick with strategic. The last two are gritty details. These are the things that justify attending at least one course on numerical analysis if you haven't done that. Now, it was Turing who said, actually way back in 1947, so that's before I even knew that computers existed, he said, if a machine is expected to be infallible, it cannot also be intelligent. Now, that's what he said, and I agree with it entirely. And that raises a question. The question is, what makes you think that a machine programmed for deep learning is going to be intelligent at all if it can't say, I don't know? You see, if what you've done is to program it so that all of these categories are the sum total of what its output can be, then what should its output be if it encounters some creature that it hasn't seen? And what should its output be if really it doesn't match a pattern very well here? It may be looking at something like a pronghorn antelope with very long horns. Is it going to classify that as a deer, which is its closest relative, or will the long horns throw it off? There are inescapable problems with software that cannot say that it has failed, especially if it's searching for things. Any interesting subprogram is capable of failing, especially those that do searches. A program that searches might fail because it's looking for something that isn't there. Or maybe it started in the wrong place, and so it should be able to say, sorry, I couldn't find it. But that means that the program calling this subprogram has to be prepared to cope with a failure of that kind without causing a calamity. So there has to be some kind of safe mode to which the program turns if one of the subprograms fails. But it's more than that. What we want are communications that tell us something worth knowing about the nature of the failure. And if you don't do that, really bad things can happen. If you look on my web pages, boulder.pdf, you'll see that not understanding a message which said something like invalid data caused an airplane to crash. Oh, they're blaming a young co-pilot because he tried to climb when he was in a stall. But the reason he tried to do that because he didn't know what he should do. And an experienced captain didn't know what to do either. It took them over 3 minutes to figure out what was happening, but the plane fell into the sea in 3 minutes. So it's really important to get diagnostic messages that are helpful. And it's the responsibility of programmers to provide them. Now, what I did, among other things, was to introduce flags and nans. Nan stands for not a number, so that if a floating point computation failed, there was the opportunity to signal the reason for failure indirectly by treating the flags and the nans as pointers. And they would point to somewhere where you can get more or less information about what went wrong. Unfortunately, that stuff isn't supported right now. I think the designers of programming languages imagine that anybody who writes a program in their language will automatically write a program that works correctly. Then we've got this problem with a naive model of the visual cortex. Well, the model is this sequence of arrays. Each array represents a plane in the visual cortex that contains a lot of neurons. And they're connected by synapses, relatively locally. Each neuron in one plane is connected to some neighboring neurons in adjacent planes, and the connections are interpreted as convolutions. And so the program that does the deep learning says, give me your scenario, and I'll somehow convert that data to a form that fits in an array, apply a convolution, possibly apply a windowing operation so that numbers that are off scale, for example, might be discarded, or they might be used to squeeze everything else down, whatever it is, and so on. And you do this until you get to the last array, and the last array outputs the classifications that you're interested in. And there might be, there could be more arrays than one for a second array, but that's not important. What is interesting is that training, which is not learning, learning is not the same thing as training. Training is what you get in a grade school in North Korea. It's called indoctrination. Okay? Anyway, so the coefficients are determined, and what you do is you minimize a certain function. I'll discuss that later. Now, here's what's missing. Logical analysis. I'll give you an example of that to show what happens if you can include it. And prompt motion detection. That's really rather important. Every creature with an optic nerve can detect motion before it figures out what's causing the motion, because the motion may be caused by the shadow of a predator, and this creature wants to flee to some safe spot before figuring out whether this predator is an eagle or a falcon, or who knows, maybe it's just a fox. So motion detection is important. And I think that contributed to this collision. I've read now about it, and it appears that the program that they used, which they thought was artificially intelligent, realized that a bicycle or something was crossing its field of vision from right to left. And as soon as it saw the bicycle wheel, even if it didn't know that it was a bicycle wheel because it couldn't see the rest of the bicycle, it could have realized that there's something about to cross its path. But no, it waited until it saw something, and then what did it see? Was it a bicycle or was it a woman? It happened to be a woman moving a bicycle. She was crossing the street, but not at an intersection. So the computer took too long to recognize what turned out not to matter much because the computer hit it. And that's an instance of that tells us that there's something else to vision beside the visual cortex. I'll give you a moment to read this. To the same extent that there's more to vision than just the visual cortex, there's more to intelligence than just imitation. Because one of the things that's peculiar about human minds, except maybe those afflicted with some versions of autism, what's peculiar about human minds is that we are capable of trying to imagine what's going on in another human's mind. In fact, as teachers, we're obliged to do that, because how can you teach students if you don't have some idea of where their minds are, as well as some idea of where you want them to be, and then you're going to try to build a bridge. Well, I'm going to talk about this a little bit. I don't think enough logical analysis is being used with deep learning. Because if logical analysis were more in use, then the patterns that we try to detect would be patterns that have some kind of diagnostic value. You might say, rather than just look to see what animals you've got, you might say, do they have hoofs? Because if a small animal has hoofs, it means it's a young horse or a young cow or a young deer. It's not a St. Bernard dog. So you can tell quickly. And similarly, you should look for long whiskers. So there's a catalog of things that we think are important in order to distinguish these animals. And that is the kind of pattern that we should be looking for, rather than saying, oh, we're just going to look at the animal as a whole, because there are too many versions of the animal as a whole. So you see, if we can figure out what it is that characterizes these animals, and put them in ovals, then that's fine. Now you've identified an animal. But if what you've seen doesn't fit, or it fits badly, so it doesn't lie in an oval, well, then you have to say, I don't know what it is. And if deep learning is to be intelligent, it has to be able to do that. So let's see what happens when we use some logic. I'll give you a chance to read this. Yes, you can look this up on the web. There's the URL. And notice this: aware of my intentions. In other words, with the aid of logic, artificial intelligence was coming closer, not perfectly, to simulate what's going on in some other person's mind, because there's only a modest number of options. I mean, you can go up or you can go down, you can turn. The number of maneuvers is finite. So it was possible to simulate approximately what's going on in someone's mind, and to do it fast enough to beat them. And that's why I think we have to combine logic of some sort. In this case, they're using fuzzy logic, but that's not important. We have to combine logic in deep learning. It's not just rote. Well, let's now look at some of these horrible details. Horrible details because we would give the same name to these things normally. This is what we want. And we give the same name to the program we write to get it. And then we get some output from the computer, and we still give it the same name, but those things are actually different. And they're different for a number of reasons. You see, the program that you write includes a number of approximations that you've been compelled to use, because the thing you want, if you really computed it exactly, you might have to know an awful lot more than you know now. When we model fluid flow, we say, here's the Navier-Stokes equations, and we set up a partial differential equation, and it does not model the flow perfectly, but well enough for most applications. And in any event, we then discretize it. That's an intentional approximation. And so the program straight F doesn't actually give you curly F. It gives you an intentional approximation. And then we then compute something. And what you compute is not quite right either. And what I mean here by a timeout, well, some programs are supposed to conduct a search. But after a while, they run out of time, and they'll come back with something. And if what they come back with is, this is where I was when I stopped, but that output is mistaken for this is what I've found, then there's going to be confusion at the very least. So this F, what is computed, is different. Now, ill condition and numerical instability, concepts that used to be blurred together in the late 1950s when I was a student, those concepts belong to different things. Ill condition is a concept that describes something about the function. If it's the function that's hypersensitive to perturbations of its input, then we'll say it's ill-conditioned. But numerical instability is an attribute of our program. It's an attribute of the algorithms we chose to use. Back in the 1950s, there were some marvelous schemes called, for example, Milne's method. Well, Milne was a respectable guy, but it turned out his scheme was numerically inconsistent. Numerically unstable. And that instability was triggered in some cases, but not all. And so it took a while to find out you shouldn't use Milne's method. But it's a characteristic of the program, not the function you want to compute. And it can be very, very hard to diagnose. So let's see, how can these things afflict us? Well, we have to find out what they mean quantitatively. Quantitatively, it's a certain derivative is the condition number, and we take a norm, which means we're measuring things now. We're measuring distance in various spaces. And when we look at an equation that says, oh, the output will be perturbed by the function's slightly different data, this is an approximation to what the perturbation will do. And so we now have an idea of how big the perturbation is compared in the output, compared with the perturbation in the input that caused it. And this is an amplification factor. And so you can think of the condition number as an amplification factor for the effect of small perturbations. Now, I have to say, not all small perturbations get amplified that much. But there are some that do. That's the way in which this norm was defined. So that says, if you're unlucky, you might have a perturbation that gets amplified enormously. Actually, if you were unlucky all the time, you'd be violating a theorem in physics, which says you cannot be unlucky all the time. But it's possible to be unlucky most of the time, and that's what happens with this coefficient. So we say that this function is said to be ill-conditioned when the condition number is huge. How huge? It depends on what you're doing. If you only want 3 figures, a condition number that adds to the error in the 6th decimal place is not going to concern you, even though you're carrying 15. But if what you wanted was 3 digits correct, and your condition number is so big that it amplifies errors so that they blot out your result because you only carried 6 figures, then a condition number of the order of 1,000,000 is going to wipe out everything. And so we have to be a bit concerned about that. And why does it happen? Well, it happens because of a singularity or redundancy or confluence. Singularity means something goes off to infinity, or if it's a derivative, it might just fail to exist. What do I mean by a redundancy? Well, if you've got a least squares problem, and it turns out that the columns of your matrix happen, the matrix represents your model, and it's where you put all your observations. And if it turns out that some of its columns depend linearly upon some of the others, or very nearly so, well, in that case, you're going to have trouble. That redundancy is going to cause numerical difficulty, which we're going to come to because it happens in our work here. And then what about confluence? Well, confluence is what happens when you're looking for the roots of an equation. Maybe you only want one of them. Maybe the equation has several. Let's hope that they're nicely spaced apart so that you can pick out an individual root. But sometimes the roots flow together. And if they do, they'll be hypersensitive to the small perturbations in the coefficients in your equation. So that's a situation with confluence. And there may be other ways for ill condition to occur, but I think I've got them all here. Numerical instability, on the other hand, now that's an attribute of the program, not the function, and it can be very difficult to debug. And that's why I have some tools which I use on my ancient computers, more or less IBM PC vintage, original Macintosh vintage. I've got them to work there, but I can't get them to work on more modern computers, partly because nobody is going to give me access to the source code of some of their compilers, and this stuff in Linux and Unix is stuff that I don't use because I regard it as inhumane, but that's a topic for another day. So it's very difficult to debug unless you have these tools that are described in my web page, and so ideally we could build them, but it would cost about 10 man-years to do the job. And 10 man-years is a little bit more than I have to look forward to at my age. So maybe some of you will read that Boulder PDF and think of it as a project worth starting. Now, how can ill-conditioned and numerical instability degrade what we're trying to do? Well, there are 2 ways where it can happen. It can happen when you supply fresh data after DL you thought has been trained and tested, and something goes wrong. And I'll show you how that goes wrong. It's a case of ill condition of one kind, not the obvious kind. And then it can also happen while you're computing the coefficients. You're trying to train it, and something bad can happen because of ill condition. And you can also have numerical instability, and I'll describe that. So how do we do training? Well, we've got to compute these coefficients. And we do that by minimizing a certain error measure, but it doesn't measure the error in anything. It measures a residual. A residual is a measure of the extent to which what you want to do isn't being done. And what you want to do is solve an equation, minimize a function, and so on. Well, that doesn't tell you what the error is, and I'll show you situations where it can't. And so now we want to minimize this function. It looks like a curly E of W, and it gauges how far the weights are from identifying all the desired patterns that you've introduced among a vast number. Vast number could be 1,000,000. Vast number of scenarios that you supply to train it. So it's an iterative process because you've got to seek a minimum. So you're searching for a minimum, and the way you search for it is you follow a downward gradient. This thing here before the prime is the Jacobian array of partial derivatives of this function. Now, because it's a scalar function, it means the derivative with respect to a column is going to be a row. But in order to get a gradient, you've got to transpose it in Euclidean space. If you're in a different kind of space, you have to do something else. Won't talk about that. And the trouble is that we're not talking about small beer here. There can be thousands of weights. So it's a pretty terrifying computation in a way. And then, just to make matters worse, there can be lots of local minima. And that is going to afflict us. So, where do these things come in? Well, as I said, it can occur after you've done the training, and it can come during the training. But after you've done the training means you've tested it. And testing is accomplished by supplying a sufficient number of scenarios that were not used for training. So you've set aside some number of scenarios, maybe a couple 100,000, in order to test the training that you accomplished with 1 million. Now, unfortunately, these things get used over and over again in the literature because people try to compare my method with your method or someone else's method, and so they continue to use the same data, both for testing and for training, which means that there's some things they never find out. What is the error rate? Well, it's the rate at which you make mistakes in classification. So if you give it a test to run classifications on, say, 100 scenarios, and it misclassifies 12 of them, your error rate is 12%, which in this business, many people would consider to be pretty good. In fact, as I'll say, my experience is that a 6% error rate has always been deemed acceptable in this domain, which is unfortunate because it turns out that if the testing data and the training data resemble each other too closely, then you'll get a very low error rate, and it won't tell you that there's something wrong. It may be that what you've got is a sharp minimum of this residual instead of a broad minimum. Let's see what happens. If you've got a broad minimum, then if you get data that doesn't quite match expectations perfectly, it will still be classified in a reasonable way by the pattern matching system because it doesn't offend the weights, so to speak, weights that were slightly different from what you've got as your optimum there. Those weights would have worked perfectly well. And so this is a case of a well-conditioned system for classifying things. But if, on the other hand, you have a sharp minimum like that, of course, it might be hard to find, but if you find it and stumble into it, now you've got a serious problem because if your data departs somewhat from what is expected, maybe only by a little, then it runs the risk of being grotesquely misclassified because you've got this very sharp minimum. That's a problem which you could address by estimating the Hessian. Now, the Hessian is normally, an array of second partial derivatives. Normally, you wouldn't compute it. But if you try to compute the gradient at a number of more or less randomly chosen places in the neighborhood of your minimum, it will give you some idea of the Hessian. At least you've got a good chance of discovering whether the Hessian is big or small. And that law of physics says you can't be unlucky all the time. So disregarding ill condition can now degrade the deep learning because this array here, which you aren't going to compute, it could be ill-conditioned. That's a different kind of ill condition. It's not a question of whether your minimum is sharp or broad. There can be another kind of ill condition at work. And this is the condition number that measures how bad it is. But we aren't going to compute H. And if we can't compute it, then how do we know that it's bad? Well, if it's well conditioned, nothing bad will happen during training. That's a rough summary. But if it is ill-conditioned, something bad will happen. This is a situation where the level lines or surfaces of that residual are nice and round like that. And in this case, the condition number is close to 1, 1.2, and everything happens quickly. The search process homes in very quickly on the minimum that you're looking for, and rounding errors hardly deflect it at all. But here's a situation which is a little bit worse condition. That's a small condition number. Normally, a condition number of 5 would be regarded as about the same as a condition number of 1. Hardly matters. This is not that diagram turned on its edge like Saturn's rings. This is what represents the level surfaces, which are roughly speaking ellipses, which are a lot longer than they are thick, except not enough. Because the more interesting case is when the condition number is a lot bigger than 10. And if I tried to plot that on the screen here, the level surfaces would look like these lines. And in particular, the minimum would be somewhere in this black line, somewhere. Any point on that black line could be adopted as the minimum because your function that measures what's supposed to be a residual, what's supposed to be an error measure, but is actually a residual. The residual is almost the same all the way along that line. So now, where's the minimizing W? It can be far away. Well, it causes this deep learning to malfunction during the training process in 2 ways. It causes the minimum weights to be computed inaccurately. And inaccurately in this case means usually rather too big. And if they are too big, that can be really nasty later, because let's suppose your weights are, say, 10,000 times bigger than other weights would have been if you had known that they're just about as good, that you get just about the same depth in that minimizing process. But because the minimum is at a long, long trough, your numerical process has had the unfortunate propensity to wander off. And there are some methods in use in the literature where this actually happens. So suppose now that your coefficients are some horrible factor bigger than they really ought to be. Let's say 10,000 times bigger than they ought to be. And in that case, what that says is that when you do the correlations, you multiply what amounts to the coefficients of a correlation matrix by your data, what you're getting is big numbers. They're 10,000 times too big. And they're going to collapse down to something smaller, because if you had good coefficients, that's what you would have gotten. And that means that there's got to be a lot of cancellation. What cancels away? It's the last 4 digits of your data that just might as well not be there, because they get rounded off when you do the multiplication. And then later when you do the subtractions, they don't come back. So this is a way in which large coefficients can hurt you, but I don't see people testing to see if their coefficients are big. So that means that their process is vulnerable to this kind of misbehavior. Which doesn't happen every day, thank goodness. And the easiest way to avoid it is there. Just carry more digits during that part, the optimization part of the computation. If you carry somewhat more than twice as many digits as you trust in data and want in your weights, then the probability of being badly misled gets to be so small that if it should happen to you, you could write a paper about it and get it published. Now, an ill-conditioned Hessian also, it delays the search process. It can delay it by orders of magnitude. And that's most painful when you're doing retraining. Retraining means you've got some fresh data and you'd like to readjust the coefficients. And why does it take so long? Well, it's because the deep learning process follows a downward gradient. And we're going to look at a few processes that do that. I'm going to look at 3 of them. Now, I know there are others. There's stochastic gradient descent that I want not to talk about until afterwards. But these are three processes I want to describe. This last one is almost certainly not familiar to you, but the first two, if you're in the business, you should be well acquainted with them. And let's see what goes wrong. Well, gradient descent is an attempt to follow certain trajectories. They're defined by this differential equation. And this too should be an exponent. There's the differential equation. And what it does is it changes this residual as you go along the trajectory by this amount, but that should be an exponent, it should be squared. I could blame my bad eyesight for that, but I won't. So that says that as you follow these trajectories, this residual function decreases until finally you get here where the gradient is 0, and that's almost always a minimum. It's possible to get hung up on saddle points and so on, but if you do, you're very unlucky. Now, what do the trajectories look like? This is a case where the condition number is only 5, and we'll look at some more later, but the important thing is this. The differential equation is not what you actually solve. What you do is you use Euler's discretization, which says I'm going to change W by an amount for a discrete time step. And that has certain hazards. Each step, sometimes called an epoch of gradient descent, it overwrites your current set of weights by a new set of weights. And this is how they're computed. But you've got to choose the step size, delta t. Well, it's called a learning rate, but we know it as a step size. And you mustn't choose it too big, because if you choose it too big, bad things will happen. You see, here is the tangent that you follow with Euler's method. You're at this point with W, you draw a tangent, and you end up there. And as you can see, if you draw the next tangent, it's going to send you back up there. And this process can be rather profound, as I'm going to say. Convergence will occur provided your time step is no bigger than 2 over the norm of h. But you don't know the norm of h because you're not going to compute it. So what you have to do is run trial and error. You try different time steps in order to see what happens. If the time steps you settle on are much too small, you'll be creeping pretty close to one of these trajectories, and it'll take you a long time to get to the minimum. On the other hand, if your time step is a little bit too big, you'll get ricocheting. You'll be bouncing back and forth. Now, if you were doing this for just 2 dimensions, that wouldn't be so bad, but you're doing it for 1,000 dimensions. So ricocheting can be happening, and you can't see it, because you have to visualize it in 1,000 dimensions. And people normally can't do that. So we've got this problem. If this is ill-conditioned, ricocheting will be severe. Let's see why. It happens because almost all the trajectories you want to follow bend sharply. And if the condition number is 50, which is not terribly big, all the trajectories look like this, except they look like this in 1,000 dimensions. And you see these very sharp bends? Well, you'd say, well, if I ever get down close enough, then it'll straighten out. But it doesn't, because if you look at this with a microscope to amplify it, you get the same picture. So you're going to be stuck with these very sharp bends if the condition number is high. And that means convergence will be terribly slow. And the people who decide in advance, the literature says that you can do 100 epochs, 100 iterations. Well, depending on the condition number, your result may be just junk. So this choice here is a delicate question. Look, the best choice is this number, and that number is the threshold beyond which you get divergence. Look how close they are if the matrix is ill-conditioned. If your matrix is ill-conditioned, big C here is big, so it disappears, its reciprocal disappears. So your step size is almost as big as is allowed. And that says that the choice to get an optimum step size is going to be a delicate issue. And it's delicate enough, and here is the reward for finding the right step size. This is the convergence ratio, which is the error in the new set of weights divided by the error in the original set of weights. And so this ratio rho, you can show that this is what you get at best if you do get the optimum step size. And it's not very good, because if your condition number is 50, it says you're knocking about 4% off of the error with every iteration, which is disconcertingly slow. But it can get worse because condition numbers of the order of 1,000 are not unreasonable. Condition numbers of the order of 1,000,000 are unlikely to happen because normally people don't carry that many figures. Normally they do the arithmetic with what we call single precision or half precision, and in that case it's really hard to get condition numbers that are bigger than a few thousand. But look, with 50 it's bad enough. Now let's suppose we do something here. We add in some momentum. That's what people say for the difference between where you are now and where you were in the previous step. And we'll add some multiple. I don't know what multiple yet, but that's just another hyperparameter that we'll have to choose by trial and error. Where did this come from? Well, it can be identified with a second-order differential equation, but I won't do that. I think it's really better to identify it with something called conjugate gradient iteration. And conjugate gradient iteration makes sense when you can form matrix vector products from the Hessian. You don't have to have the whole Hessian in memory all the time. You just have to have enough of it in memory so you can multiply the Hessian by vector. And if you can do that, then you can get conjugate gradients to work. And the nice thing about conjugate gradients is you don't need formulas for the hyperparameters delta, tau, and beta, because they get computed as you go. So that's marvelous. But we don't normally have access to the Hessian. And so we have to just simply try to find constant values for these hyperparameters. They depend upon the Hessian you don't know and the condition number you don't know. And if you did know them, then here's the formula. That would be the best beta. And here's the formula for the best delta tau. And here is the convergence ratio. And this convergence ratio is enormously better than it was for gradient descent without momentum, because even if the condition number C is just 50, which is very modest, then with ordinary gradient descent, you're going to knock 4% off the error. But with momentum, you're going to knock the error down by 25%. And that really makes a lot of difference. Now, anadromic gradient descent is yet something else, not widely known. The word anadromic comes from the Greek for running back. We have some fish, the salmon, they're called anadromous fish, and there's some trout that do the same thing, and they insist upon depositing their eggs somewhere in the stream where they were born. And that's becoming more and more problematical, but that problem is a talk for another day. So I've co-opted the name anadromic for these schemes because people used to call them sometimes reversible or reflexive. But they also use reversible and reflexive for the differential equations, and so the heck with it, I just chose a different name. Now, what happens is this. If you take these discrete steps, possibly at varying lengths, and you get here after going forward, and they say, no, I want to go back. In order to get back with an anadromic method, what you do is reverse your steps, reverse their sign, and reverse the order in which you use them, but otherwise you use the same formulas as took you forward. And it turns out that that actually helps. It means if you use it, that method will give you accuracy that would, if computed by a non-anadromic method of comparable complexity, be worse. You get better accuracy this way for a given price. So let's see what we can do with that. Of course, in order to construct an anadromic method, as I said, sometimes that becomes unobvious, and what we have to do is take our inspiration from Hamiltonian differential equations that are used to solve for the motion of mechanical systems without friction, like the planets, for example. Although I've got to say that the planets do suffer from passing through residual gases and from tidal friction and other things, but there's a very close approximation, sufficiently close that most people don't notice that the moon is actually getting closer to the Earth with every day. But not so much closer as matters yet. So, here is this Hamiltonian, which would be conserved as you move along a trajectory, because the derivative as you go along a trajectory is 0. That usually represents energy, potential energy, depending upon the position variable W. But you also conserve all sorts of other things. You conserve kinetic energy and, well, actually it's the sum of kinetic plus potential energy that you conserve, and you conserve angular momentum and linear momentum, except angular momentum and linear momentum are complex things. They are arrays, they're vectors. So these things get conserved, and that's not what we want, because we don't want a trajectory that goes on and on and on and on and on, around and around. We want a trajectory that heads for our goal, which is minimum. So we've got to introduce friction. And when we introduce a little bit of friction, if we introduce a reasonable amount, then this is the Hamiltonian. Okay, there is our potential energy, and here is our kinetic energy. This thing here is just simply a scalar product of a vector with itself. And here is our differential equation, the Hamiltonian equations, except there's an extra term there for drag. And that extra term means that when you differentiate the Hamiltonian along a trajectory, you get this. And this is negative as long as the vector v is non-zero. When the vector v vanishes, you're at a stationary point. If the stationary point is finite, if you don't wander off to infinity for some reason, if the stationary point is finite, okay, then it turns out the gradient vanishes there too. You're at what is almost surely a minimum. And so here is reprise. These are the differential equations. And the question is, what do the trajectories look like? Well, the fact is that the trajectories look about the same as before, depending on the condition number. And if the condition number is just 5 and the drag is big enough, then this is what you get. If it looks familiar, and with big drag and a high condition number, this is what you get. Oh, that's going to be a problem, isn't it? Well, what if you have small drag? Well, small drag and small condition number, the spirals really go in fairly quickly. So convergence should be pretty fast, whereas if the condition number is 50, the spirals are too tight. They go around too slowly, and that causes a problem of slow convergence. So let's look at the actual algorithm. Now, the algorithm is known to physicists as the leapfrog method, and they've applied it to differential equations called symplectic, and it turns out that all sorts of things are conserved there, but the fact is that this is also an anadromic scheme, and that is why it'll be useful for us, because as an anadromic scheme, the principal cost compared with gradient descent is in this division. You divide by this scalar. That's what causes the scheme to cleave closer to the trajectories. How much closer? Well, it's of the order of step size squared. So as you make the steps smaller, the departure, this is the derivative. This is the derivative of the Hamiltonian, approximately, in the midway between the new and the starting vector. And this is the vector v average, it's somewhere between the original and the new. And it turns out that the differences all turn out to be of order delta tau squared, whereas for a non-anadromic method of comparable complexity, the error would be of order delta tau. That's the advantage. It says if you have a sufficiently small step size, you're going to get better accuracy from the anadromic method. Of course, you don't want accuracy in following the trajectory. You just want to get to the goal. But the trajectories bend, and so you have to follow them. And that following gives you two things. It reduces the ricochet, and it gives you the same rate of same ratio of convergence as you would have gotten for gradient descent with momentum, but it's easier to find the hyperparameters. That's the principal advantage to the anadromic method. And I should add that we can see why that happens when we plot minus log rho. You see, rho is a number that will be typically a little bit less than 1. And so minus its logarithm is a positive number. And the bigger that number is, the faster you're going to go. So let's look at what happens with an anadromic method. Here's a plot of that logarithm. And it obviously the optimum is there. But more important is that if you get a little bit off in the step size, you won't suffer too much. On the other hand, if your drag is too big, the drop is precipitous. So don't overdo the drag. And then you can vary the step size, and you'll get reasonably good convergence rates. Whereas, if you do it for the gradient descent with momentum, look what happens. If the step size gets a little bit too big, you plummet. So that means that choosing the right step size is more difficult. More difficult because if it's a little bit too big, you're gone. The same thing happens if the condition number is 50. Same type of phenomenon. That's what happens if the condition number is 50 to gradient descent with momentum. So we come to the conclusions. And that's what a numerical analyst would recommend. Okay.
Do we have any questions? There's probably a mixture of practitioners of machine learning and numerical analysts and lots of other people here, so I think it's all fair game.
So did I capture correctly that in seeking an optimum, that you should be continually adjusting the step size and actually have some friction in the way it adjusts? Is that the main point?
Well, I call it friction in the anadromic method.
Of course.
But it's about the same as that parameter beta. It's just one of the hyperparameters you have to deal with. And you can't deal with it happily without knowing something about the Hessian. And there are optimization methods that estimate the Hessian by keeping a historic record of the variations in the gradient, because the derivative of the gradient is the Hessian. And this is like Fletcher-Powell methods and so on. And we can't use those here because you've got to keep too much storage. If you're looking for 1,000 weights, you're going to end up with an awful lot of storage as you try to retain the past history. And it's also somewhat messy to compute because that past history doesn't always reflect the Hessian accurately. So we normally don't compute the Hessian. And we don't normally approximate it. But it's a good idea to approximate it when you think you're finished, because you have to distinguish between a shallow or broad minimum or a sharp one. And the only way to do that is to get some estimate of the Hessian, even if it means rolling the dice to find out.
just to follow up on that one, do you think that because of the structure of neural nets, there might be some structure in the Hessian, of which we know there's many structures matrices can have, that would make it easier to estimate?
Well, you've got to compute what amounts to a sequence of derivatives and combine them. If you can represent this error function as a sum of error functions, but they're really residuals, if you can represent it as a sum of residuals, that in some respects makes things easier, but not easy enough. I haven't found anybody who's willing to compute the Hessian except if the dimensions are rather small, maybe 100 or so. If the dimensions get up into the thousands, then it's a computation that nobody really wants to fight with, because there's an enormous amount of arithmetic to be done, the square of the dimension. So I think I've gone through methods here which are widely used, except for one of them. I said stochastic gradient descent. We can talk about that later if anyone cares. But of the methods that might widely be used, there's the anadromic scheme, costs about the same as the method with momentum, as far as storage is concerned, about the same as ordinary gradient descent, as far as arithmetic is concerned, because the cost of arithmetic is trivial compared with the cost of fetching things from memory and putting things away. So gradient descent it's just simply too slow. And anadromic gradient descent, you have a decent chance at finding your hyperparameters.
Here's a question that ties to that very last comment you made. You've spoken earlier about sometimes using double width precision to compute things more accurately, hoping to get what you're looking for. Yet people in the name of economy of space and time are using very narrow types, 16-bit types, sometimes with 2 decimal digits of precision, which is very much the other direction. How do you reconcile?
Well, it may very well be that when you find the coefficients, it isn't worth keeping very many digits, because they're going to do just as well with, say, 6 bits or 8 bits as they would do with 16. And so there's no reason to store the coefficients to high precision. But to find them, that's a different matter. And with all optimization problems, you run the risk of ill condition. And the only way to address that is to carry twice as many bits plus a few as you trust in the data and want in your answer. That's your cheapest insulation. You want to get away with the same number of bits in your arithmetic for finding the coefficients as you use when you store them. In that case, you're going to have to find an error analyst. And I should tell you that an error analyst with a PhD, that'll be expensive. And it may not help you in the end. Because sometimes, even as an error analyst, you might be overmatched by the problem. So my recommendation for carrying double plus a few bits is it's much cheaper than thinking.
So for anadromic gradient descent, is there any real guarantee that you would converge to a broad, to a voluminous minimum? Or
Okay.
It seems like this is something that would be happening in practice. Do we know how to analyze it? And either way, what is the intuition for it?
Well, anadromic gradient descent will get you to the same place as the other gradient descent schemes do, except if that place isn't one place. If there are lots of minima, it's very hard to say which one you're going to get. And so if there are lots of minima, it's a good idea to look around and see how many are there. And are some of them sharp and others broad? Because that's important for their application. And whether you find sharp ones or broad ones is not a property of the algorithm you choose. It's a property of your problem. Although there are some algorithms which have been found to get you to sharp minima with one version of the algorithm. It's called batch size. Big batches seem to get you to sharp minima, and small batches get you to broad minima. But that's just a problem arising because there's so many minima. And so what you get depends accidentally on your algorithm. And in any event, I don't believe everything that they've written up, even though some of it is written by a former student of mine.
I just had two questions. The first would be, have you looked at Quasi-Newton methods, or do you think they'd be too expensive in practice? And the second would be, what about methods with regularization? Would that have any improvement on?
All right, I can answer the question about regularization. Okay. Regularization is a way of preventing the weights you compute from wandering off to infinity.
Right.
But the trouble is that now there's a regularization parameter you have to choose. Oops, another hyperparameter. Okay? If you make it too big, you'll end up with weights that are near the origin, regardless of whether they make the residual small.
Right.
And if you make it too small, well, then it won't rein in the weights. So what should the value of this be? The problem has been addressed frequently in the past. It used to be called Takanoff regularization. And NASA used to get pictures of the moon, which were somewhat ragged, noisy. And so they try to smooth them. And that smoothing is essentially applying this regularization. Of course, if you smooth a little bit too big, then all the hills look sort of, gradual. And, it looks like a fairly tolerable geography, tolerable topography, I guess is the word I should use. But if the regularization parameter is too small, then everything turns out to have cliffs and spikes. There are cliffs and spikes on the moon. What is the value of the regularization parameter that would show you that? Here's how they choose it. Imagine your regularization parameter is a knob on a dial, and you're looking at a screen, and you turn the knob until you like the picture. Now, you also had another part to your question which came before this. What was that? Say it again.
Oh, I was wondering about Quasi-Newton methods to approximate the Hessian instead of using gradient descent.
Say again what?
Quasi-Newton.
Quasi-Newton. Quasi-Newton means you're getting an estimate of the Hessian somehow.
Yes.
And for small dimensions, I think that's very reasonable. For large dimensions, the cost of getting the estimate of the Hessian, which you have to get in a sufficiently large dimension, that can be problematical.
Right.
I don't know how well that would work. I don't know if anyone's doing it.
Okay, interesting.
Do you?
No, I haven't seen it in deep learning much at all, just more in the optimization community.
Yeah. So I don't have any experience with that. Of course, my experience is secondhand because I meddle with graduate students.
Sorry, this might be a little repetitive because people asked about SGD before and also numerical stability. So we know conjugate gradient itself is not numerically stable, but there is a trick to make it numerically stable.
Actually, conjugate gradients is stable in a perverse way. Conjugate gradients would ideally terminate after you've done as many iterations as the dimension, actually as many as the rank. It can converge really fast.
Okay.
But because of rounding errors, that's what bothers you. Conjugate gradient iteration seems to go on and on and on and on, well past the number of steps equal to the dimension. And I think it was Anne Greenbaum who discovered that what actually happens is that your iteration behaves as if the dimension of your matrix were some modest multiple of the actual dimension. So if you have a matrix of dimension 100 and you expect to stop after 100 steps, the way that the iteration behaves is it may take 1,000 steps. And it converges at a rate which is appropriate for the same distribution of eigenvalues, but repeated, as if every eigenvalue was repeated, say, maybe 100 times. And so it isn't really numerically stable until you come close to the end. Now, that's the problem. Where is the end? Because if you go on for too long, and Greenbaum and company more about this, if you go on for too long, what happens is that you get swamped by rounding errors, really swamped, so that when you compute the residual, it's almost entirely junk. Rounding error. And when that happens, then you can get divergence. You can get locked into a situation where somehow, if you keep on iterating, you go off to infinity. So the critical thing is to make sure you stop before the rounding error overwhelms you. Come visit me and I'll show you how to do that.
Thanks.
Okay.
Are there any other questions? Do we have any other questions? Well, it sounds like if there are, you can go to Belleville's office hours. So thank you very much.
Okay.